Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. In this course, we have been exploring the depth and the breadth of organometallic chemistry, particularly with regard to the applications of organometallic compounds in large scale industrial processes. In this context, we have looked into various types of organometallic reactions which have been practiced in large industrial scales, and to start with we have looked at REPI chemistry, which is the conversion of C2 feedstock or acetylene to other functionalized forms. So, after REPI we had been looking into another very interesting reactions, which is olefin metathesis. We have looked at olefin metathesis followed by alkyne metathesis, and now we have been discussing about cross metathesis reaction, which was taken up in the previous lecture. Now, cross metathesis reaction, as we have been discussing, is been developed or has been developed in conjunction with industrial process, particularly SHOP, or which is better known as Shell higher olefin process, and which was mainly used to utilize unwanted feedstock from this SHOP alpha olefin oligomerization process. So, let me just illustrate this. Or Shell higher olefin process would convert ethylene to alpha olefin using nickel catalyst. Now, these alpha olefins was a primary source which was from ethylene feedstock, and this was used or had use for making had requirement for making soft detergents, which has long chain fatty alcohols. Linear fatty alcohols. So, prior to these alpha olefins, they were accessed through cracking as well as hydroformylation of alpha olefins, and they were synthesized from other methods, and SHOP provided a easier and convenient access to this alpha olefin other than the prevalent method of cracking or from alkyl halide sources that gives alpha olefin and then the hydroformylation to this. So, this was a better method to get alpha olefin, but the only problem which arose was that it was churning out alpha olefins of various fragments from C4 or to C12 to C18 to C22 and so on forth. So, a large range of oligomers were obtained, and this was best represented by the Schulz-Fleury distribution. C12 C18, and the distribution was something of the type this. The now as for the requirement for detergent was in this region, which are about 40 to 50%, and they were for making detergent range. So, cross metathesis was then cross metathesis, actually cross metathesis followed by isomerization, another reaction. So, cross metathesis as well as isomerization was used to convert the unwanted lower fragment and the unwanted higher fragment to make something of within the range of C12 to C18 for the use in soft detergent applications. So, this is where the cross metathesis reaction came into being, in the sense came into being applicable for using the distribution of alpha olefin, which otherwise at that point of time was not usable for any commercial purpose. So, this was an interesting development which was practiced in a large industrial scale way back from 1977 in the shop plant, and this shows how this cross metathesis reaction was employed in large scale for commercial purpose. So, I am going to illustrate this cross metathesis has been used with shell higher olefin process in industry since 1977, and this is given nicely by this reaction which is a C4 fragment plus C10 H21, this is C22 fragment in presence of molybdenum trioxide, it is molybdenum oxide catalyst, and Al2O3 giving 2 of these C13 fragment, and this was actually both E and Z mixtures were obtained. and as mentioned that the process actually involved, the industrial process involved indeed 3 process combination of oligomerization, isomerization, and metathesis reactions. Now, these 3 processes had been discussed in details in our previous lecture, and the reference for this is by an article by William Keim. Wilhelm Keim in Anglichem International Edition, (2013), 52 12492 2122496. The catalyst was MoO3 Al2O3 for cross metathesis reaction, and then as we had observed that metal carbene species are usually involved in metathesis reaction, then the question which comes to mind that how does a metal oxide in terms of molybdenum oxide carry out cross metathesis. So, there is a interesting question in the sense that for the cross metathesis large scale reaction, the pre-catalyst was originally used was molybdenum trioxide, and what it turns out that the active catalysis species of molybdenum carbene is generated through the following reaction as is shown below. The active molybdenum carbene species is generated at the catalyst surface as is depicted below, and this is shown by the equation given here. This is molybdenum oxide reaction with olefin giving the molybdenum carbene species as is shown here with a bound ketone, and this is the active species and this is the pre-catalyst. So, what is seen over here is that the pre-catalyst of molybdenum oxo reacts with an olefin to generate the active species along with a metal carbene, a metal along with a ketone, and this active metal molybdenum carbene species then carry out then it carried out this cross metathesis reaction, and this cross metathesis reaction had been developed with the intent to use the higher and the lower alpha olefin oligomers to produce mid range alpha olefin oligomers which could be converted to detergents like fatty acids or through or fatty alcohols as required through the process of another important industrial scale organometallics reaction, and which is hydroformylation. So, what we see is a chain of reactions, all of them are performed in large industrial scales, and they are effortlessly used for converting one feedstock to another to finally what is the valued target that is being achieved. So, hydroformylation of shop alpha olefins which is of the range C12 to C18 would give fatty alcohols for detergent applications. So, one thing to note here is that right now it may seem that something as trivial as application in detergent industry was brought about such a utility of so many different reactions, so many different nice organometallic reactions for the large scale production of the feedstock for detergent industry. So, what we see is that the organometallic chemistry can cater to all aspects of societal need, be it from detergent to polymers to so on and so forth, and all can be brought about by the application of a very intriguing set of organometallic reactions. So, here we see that how cross metathesis along with isomerization, SHOP and hydroformylation, 4 processes practiced in large scale would finally give feedstock for producing detergent for the societal market. So, with these let me just talk bit more about the advantage and disadvantage of cross metathesis reaction, and what it turns out is that the limitation of cross metathesis reaction arises due to the non selectivity in products in terms of not being able to exclusively form one of the product whether that be E or Z. So, one of the limitations of cross metathesis reaction is that the both E and Z products are formed in a mixture and that gives rise to less selectivity in product formation, and hence in more challenges in product isolation. So, this I will illustrate by the equation as is given below. Cross metathesis has limited applications due to the formation of mixture of products like branching, homodimer, and easy mixtures. So, this is given by the equation as is shown here. R1, R2 catalyst, C2H4. Now, the cross metathesis of these two catalysts can result in so many different products as is shown here. R2, so it can be R1, R2, and that can be easy mixture, and that is given by this wedged bond plus R1, R1. This is a homodimer, again easy mixture plus R2, R2 easy mixture. So, the main the drawback is what we see that the selectivity is less, that all of these come at both easy olefinic mixture. This is the real cross metathesis product, and so this is the cross metathesis product, and these are homodimers. So, the selectivity is a key issue of cross metathesis reaction. And hence, one of the important challenges is the ways to increase this selectivity of cross metathesis reaction. Challenges is to devise ways to increase the selectivity of cross metathesis reaction. And in this regard, important is to mention that Grubbs found a way of increasing the production of heterodimer while starting with the homodimerization first. So, this is nicely illustrated by the equation over here. Grubbs reported increased yield of heterodimer while one of the starting olefin underwent homodimerization. This is best shown by the equation given here. So, R 1 Grubbs catalyst. So, the first step is elimination of ethylene. R 1 this is nothing but homodimer. Now, when this reacted with R 2 which also eliminated ethylene, then R 1 which is heterodimer. So, Grubbs the point to note here is that in this sequential two step process of introducing the olefin sequentially, Grubbs reported increased yield of this heterodimer. So, this is one way of improving the selectivity of this cross metathesis reaction. Then the other way of increasing the selectivity of cross metathesis reaction is partially by carrying out the reaction through immobilizing one of the coupling partner. This is best given by this sentence. The selectivity of cross metathesis can be improved by immobilizing one of the coupling partners, coupling olefin with a polymer, so that the cross metathesis product remain there and the soluble HOMO dimer metathesis product is separated out. So, the other way of increasing the selectivity of cross metathesis product is by immobilizing one of the olefin, so that the cross metathesis product remain in the polymer and the soluble homodimer product is separated out. So, with this I come to the conclusion of today's lecture. In this lecture we had looked into the application aspects of metathesis reaction with regard to the Schwab olefin polymerization process, and what we had discussed is the fact that all these large scale industrial reactions have been used for making feedstock for soft detergents or fatty acids, and how cross metathesis was developed to utilize the non usable alpha olefin fragments of low and high molecular weights to produce alpha olefins of medium range molecular weight, which could be used for applications as detergent. We have also looked at the issues which remain which plague cross metathesis reaction, and one of the main issue is the selectivity, issue of selectivity, because the metathesis does not distinguish between the two isomers E and Z, and both are formed in the mixture for each of the products like cross metathesis products as well as dimer homometathesis products. And then we had also looked at various attempts been made to overcome this lack of selectivity issue, and two such methods that we have discussed is one by Professor Grubbs, who had reported increased yields of cross metathesis product by allowing homometathesis of the first olefin followed by the introduction of the second olefin to give the larger amount of the cross metathesis products. We have also looked at another strategy that employs immobilizing one of the coupling partners on a polymer. So, the cross metathesis products stay stay on the polymer surface, whereas the soluble homodimer metathesis products are separated out. So, with this we come to conclusion of today's lecture. We are going to be talking more on the aspects of cross metathesis as well as some other olefin metathesis reaction, particularly the ADMET reaction, when we take up our discussion in the next class. Till then, goodbye and thank you.